we're going to look at an example, which is example 4.61 in the 3rd edition. I will post what it is in the 4th edition. It's in chapter 6, the first example in chapter 6. So we want to consider a 3-member truss. All the members have identical cross sections A, and modulus of elasticity is E. We have hinge support joints at A, B, and C, allow for free rotation of the members about the z-axis. We wish to determine the horizontal and vertical displacements at joint C and the forces in each member of the structure. So step 1 is to generate our element level global stiffness matrix. We're going to do this using MATLAB. And to do that, we need to know our angles. So we're going to determine So you determine your angles by rotating all of your members the same direction from a common coordinate system. So this is our coordinate system XY. So for member 1, it gets rotated 0 degrees. For element 2, it's rotated 90 degrees. And element 3 is rotated 45 degrees. If you had a member that went past 90, so say I had a member over here, that would be, say, 135. Now that we have our angles, we can use MATLAB or your preferred coding method. I'll post a MATLAB code online and explain it. We would get that our stiffness matrix for element 1 is equal to EA over L times 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0. Because it's not rotated anything. For element 2, it's going to be EA over L times 0, 0, 0, 1, 0, minus 1, 0, 0, minus 1, 0, 1. So that's the 90-degree rotation. And for element 3, it's going to be EA over L times 0.3536, 0.3536, minus 0.3536, minus 0.3536. Because that's what it comes out to be for 45 degrees. So next I want to look at my nodal displacements. So my horizontal displacement of element 1 at node 1 is going to be my horizontal displacement of element 3 at node 1. We're going to call this U1. We're going to have the same for our vertical displacements. N2 of element 1 and N1 of element 2 join up at U2. That's V. And N2 of element 2 and N3 of element 2 join at U3. So we really want to see what's connecting everything together. So we look at our forces. We have F1 in the x direction plus F3 in the x direction has to be equal to F1x. The same thing goes for y. F2 plus F1 2x has to equal to F2x. Same goes for y. And then for F3x, we have F2 N2x plus F3 2x. And the same in the y direction. So we know our global forces, we know our global displacements. Now it's time to assemble everything together. So we want to see how are things related. So we're going to assemble our global stiffness matrix. We're going to do this in a similar way that we were with discrete systems. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. It's a 6 by 6 because we've got to remember that we always have an XY, an XY, and an XY. Okay, and this is also node 1, node 2, node 3. So the first thing I'm going to ask myself, well, what's at point 1? Well, at point 1, we have elements 1, and we have elements 3. And they are end 1, so I'm going to put my double subscript in. I'm going to assemble the diagonal because the diagonal is, I'll go across the row. So then I have one x and one y. So I'm going to add 1. So I still have elements 1 and 3. I'm still at end 1, but now I'm in the y direction. So I want to add 1 to the second subscript. So now I'm asking myself, well, what connects points 1x and 2x? Well, it connects points 1 and 2 in the x direction is element 1, so K1. And then same for the y. Now I'm adding 1 as I go across the row, because if in the local 4x4 matrix, N2 is now in rows and columns 3 and 4. So we've expanded our view. So what connects points 1 and 3? Well, that's element 3. So once I do the first row, I'm just going to copy it. And I'm going to add 1 to my first subscript everywhere. So I want to keep going. I'm going to ask myself, well, what connects points 2 to point 1? That's still element 1. And this time I'm going from end 2 to end 1. That's also element, no, sorry. Same for the y direction. So now I'm at point 2, and at point 2 I have elements 1 and 2. And end 2 of element 1 in the x direction, that's 3. And end 1 of element 2 in the x direction, that's 1. And then what connects points 2 and 3? Well, 2 and 3 are connected by member 2. And again, I'm just going to copy the elements for my next row. And add 1 to the first subscript. I'm going to do my last one. So what's connecting points 3 and point 1? Well, points 3 and point 1 are connected by element 3. And that's end 2 to end 1. What connects points 3 to points 2? That's element 2, again from end 2 to end 1. And then at point 3, we have element 2 and element 3 together. And it's end 2 for both of them. Then I'm just going to copy it and add 1. This is a typo. This should be a 2, 3, 1. Sorry, 3, 2, 4, 2. So we have our assembled matrix here. And of course, this would be multiplied by our displacements U1, V1, U2, V2, U3, V3. And that's going to be equal to our forces of F1x, F1y, F2x, f2y, f3x, and f3y. So what I have to do now, we're going to apply our boundary conditions. What are our boundary conditions? Well, u1, v1, u2, and v2 are all equal to 0 because they are fixed. We have f3x is equal to p, and f3y is equal to minus 2p. So we're going to have our condensed system of equations. We're going to delete rows and columns 1, 2, 3, and 4, since they multiply our known zero displacements. So our condensed system is going to be, our condensed system is just going to be this little portion down here. So it's K233 plus K333 times U3 and V3 is equal to P and minus 2P. So you could go back and not go back. You can use a matrix solver to solve for U3 and V3. Once you know U3 and V3, we're going to solve for the reaction forces. And we're going to solve for the reaction forces using the rows from columns 5 and 6 that we previously ignored, or you can use the full system. You should get the same answer. But f1x, f2x, f1y, f2x, f2y is equal to K313, K323, K213, K223, times U3, V3. And that's going to give us our F1x and our F1y. Lastly, the problem asks us to solve for the stress in the member, so we're going to go back to local. So we're always going to go back to local in the end. To go back to local, we need, to be able to calculate our stress, which is our force over our area, we're going to need our local displacements, and we're going to get our local displacements by taking our global displacements and converting them back. So I'm only going to write it for element 1, but UE1 bar, VE1 bar, I'm going to do it for element 1. So the displacements for element 1 are going to be our transformation matrix for element 1. Times our known Now, someone point out that this is U1, this is V1, and those are U2 and V2. Your answer should be number 0, number 0. Oh no, sorry. If I ask for the reaction forces, you would do F bar is equal to K local EA over L times K local U bar, where K local is 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0, always. And this should always be some number 0, opposite of some number 0, because of the way the force displacement relationship is designed for a truss. So that's trusses. I want to make another example video for more trusses. And this is really where MATLAB and indice notation is going to come into play.